Hi guys, how's it going? Today we'll be going over maximum, minimum, both relative and absolute. We'll be going over how to look at it from a graph and how to go through it with just the function. So without further ado, let's get started. So let's say this is the graph of a certain function f of x. The main idea of trying to find what it is through f prime of x, through the idea of f prime of x equals 0, is that when you take because like f prime of x is the slope of f of x at each point, so we keep going, and then at a certain point here, the slope is going to start evening out, it's going to lessen, and then at one point it will be 0, and that point is the maximum before it starts going back down, right? So this point right here, when the slope is equal to 0, is going to be where it's going to be at a maximum, minimum, or in this case it's going to be a saddle point, which we'll get into a little bit later. So here we can see that if you draw out the graph of the derivative, we have a very positive graph. So very positive, but it's slowly decreasing to 0. Say it goes to 0 at 0, right? And it is a very negative slope, so it crosses there. Very negative. And then it starts to even out at this point right here. So we'll say it crosses back over at 0 because the slope right here is 0 as well. So there we go. So it starts increasing again. Positive. It's positive, it's positive. Now it starts to decrease. And then at this point it's going to be 0. Then there's a positive slope after, so it's going to go back up. So through this, we can see that our relative, well, from our first graph, we can identify these visually, that this is going to be a maximum, and this is going to be a minimum. Now, since I didn't put any bounds on the first function, we don't know if it's relative or absolute. Well, we can't really find absolute, maximum, min right now, so we could just call these relative. But see how at this point, the slope is equal to 0, and that will be our maximum. So it will always be a maximum when the f prime of x goes from positive to negative. The critical point, which is when f prime of x equals 0, will be at a maximum. And vice versa for the idea of a minimum right here, right? So the slope goes from a negative slope to a positive slope. And so visually, you look at it from positive slope, and then to a negative slope, there's going to be a 0. But for a minimum, it's going to be negative slope, then a positive slope, and then you will get a 0 slope right here. Okay, so that's cool, but what if we are only given a function? Can we do something with it? Well, this is when it starts to get a little trickier, because from a graph you can visually see a maximum and a minimum. Even if they give you the graph of a derivative, you can easily find it. But with only a function, it gets a little bit more complicated. So we're going to take this one, a basic function that we can graph out on the side, but let's pretend we don't know how to graph it to start with. And so we start with the idea of a critical point, f prime of x equals 0. So we'll take the derivative and set it equal to 0. So derivative of x squared is 2x. So 2x equals 0 and x equals 0. Okay, so we know that at point x equals 0, if you want to find out what it is, 0, 0, we know that there's going to be a critical point. Now, do we know if it's going to be relative min, relative max? We don't know. Not yet. So what we want to do is take the second derivative of f of x, and that will give us the concavity of our graph. So if it's concave up for f of x, that means that the graph will either look like this or like this. If it's concave down, the graph will look like this, or it could look like that. So the main idea of looking at this is that if the graph is concave up at this point, it's going to do something like that. And so with this, we know that we have a critical point at 0, they'll show us that we indeed have a minimum. So, rewritten differently, if f double prime of x is negative at the critical point, then the point will be a maxima. And vice versa if f double prime of x is positive. If it's positive, which it is in this case, it will be a relative min, or a min. We don't know if it's relative or absolute yet. And so we could say that the point 0, 0 is a minimum. And since we do know how to graph it, we can check. We have a graph here. That is a terrible graph. And so, first thing we want to check, is our critical point in the right place? It's right here. Yes, it is. Okay. And does it look like it's a relative min, as we can see from the graph? So, we did our job correctly. But we must acknowledge that not all critical points will be a min or a max. As I said before, sometimes it will be a saddle point. And let me show you what I mean. So, let's take the graph of f of x, or the function f of x is equal to x cubed. So we go through our path, right? So f prime of x is equal to 3x squared. Take the derivative, is equal to 0. Okay, so we solve it out. We end up with x equals 0. But when we take that second derivative, f double prime of x is equal to another power rule, x squared, 6x. So now when we plug in 0 for x, f double prime of 0, our second derivative is 0. So that implies that it's not positive or negative for the concavity. Which, let me draw the graph on the side. Makes sense, because there's a point where we call an inflection point, where it changes from a negative concavity to a positive concavity. And the main idea here is that when it is at an inflection point, or when f double prime of x is equal to 0, there will be a saddle point. So it was not going to be a max or a min, as you can see from the graph, but rather it's just a random critical point, just a saddle point. Which is very important to look at, because when you do look at all your critical points and you don't look at the second derivative at all, it starts to get pretty muddy about there, because when you don't test it out, you don't know if it's a relative min or max. So it's very important to either visually see it in your head or just write it down, see if your ideas are correct or not. Now let's jump into the idea of relative max versus absolute max and relative min against absolute min. Really, these come into effect most of the time when you have bounds on either side of your graph. So let's chop into one problem. Okay, so now we have our function and we have our boundaries. So let's start doing what we do. Let's find some critical points. So g prime of x is equal to x minus 4. Okay, so when we set this equal to 0, 2x is equal to 4, and x is equal to 2. That's one of our critical points, and it's between it's in our interval. So we know that 2, comma, negative 4 is a critical point. And if we go one step further, we'll know if it's a relative min or max. So we plug in 2, or sorry, we take the derivative first, I should say, and we just end up with 2. So it's going to be positive. The concavity here is going to be positive. So since concavity is going to be positive, we're going to have a min. Now, is it going to be relative or max, absolute? We don't know. But here's how we can find out. The idea with absolute min and max is that not only do you have to look at all the critical points that you could find like that, but you also look at the bounds itself. Because if you have a function like that, you can have a relative maximum here, but it's not going to be the absolute maximum, because if you're cutting it off at this point, this will be the maximum, which is the endpoint. So always, 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 always check your endpoints when they're asking for absolute min or max. So let's test it. We have a minimum here, but we plug in 1 here, so g of 1 is equal to 1 minus 4. Let's go to negative 3. Okay, so we got 1 comma negative 3. So far this one is still the absolute min. Let's test the other one. G of 3 is equal to 9 minus 12. Is equal to negative 3. Okay, so from here, we can deduce 3 comma negative 3. We can deduce that this will be, in fact, an absolute min, because we've tested the endpoints. So the correct way of writing this out, let's say if you're on a test, would be the graph of g of x has a absolute min at x equals 2 and is negative 4. So you could say this, or you can invert it. You could say the graph of g of x has is an absolute min at y equals negative 4 at x equals 2, if that makes sense. Just writing out a statement showing what you found can be very important. Now, I chose a problem by accident that didn't have an absolute, that the endpoints were an absolute min or max, so it kind of gets a little muddy, but I hope you guys can see how the endpoints have to be considered when you do look at absolute min and max. Not so much when you look at relative or critical points. If it's a critical point, you'll know, but it's very rare. I hope this made sense. The AP test likes to put always a question about a graph and where's the minimum, maximum, all that good stuff on the problems. So we'll be going make another video about this and exclusively looking at an AP question and work it completely out if this didn't make sense. So be on the lookout for that. Hope you enjoyed and hope you learned something. Thanks for watching.